Recording is rolling. It is Tuesday, January 7th. We're going to finish this Geneva Drive project from yesterday. Now, actually, before I do that, I do want to give you guys a little bit of lecture notes. So, looking at these thumbnail notes, I have full PowerPoint slides for these. I want to go through some of these. This morning, I was hoping I would have some time, and I did about 15 minutes at the end of class. But I think a better arrangement of the class is to actually do these up front at the beginning, because I want to plant some of these ideas, like what is rotational inertia, what is torque, so that you'll have like a couple of nights to sleep on this, and then that'll help you out by the end of the week. Okay, and then the last part of class, like the last about 35 minutes, we could just full focus on this Geneva Drive project. Okay, and of course, I'm not going to be here tomorrow. What I'm going to leave you guys with tomorrow is a Radio Lab audio story. Now, I'll give you guys a worksheet too, just to help you guys follow along. But really, you guys get to hear a really cool story about science of music and sound. The worksheet just helps you follow along and keep track. You guys turn that in at the end of class tomorrow, then I'll give you guys credit for that. All right, so give you guys a little bit of lecture notes here on rotational dynamics. Got a PowerPoint version here. Okay. Now, the first few slides here, some of this is going to be reviewed. Some of these slides you guys saw last semester, but maybe we only looked at like half of this. For example, this first slide, I have some rotation motion variables and units. In the top three lines you guys saw last semester. I guess if I flip forward a little bit, you guys remember this turntable physics from last semester? Now, last semester, we mostly just focused on the kinematic aspect of this. So this is turntable turning. How far is it turned? We'll call it angular displacement. That's the Greek letter theta. How fast is it rotating? We'll call it angular velocity. That's Greek letter omega. And if it's speeding up or slowing down its rotation, we'll call that Greek letter alpha for angular acceleration. Okay. So go back a little bit. Okay, there's the units for each of those. Boom, boom. Oh, now the bottom half of this table, rotational inertia, that's capital I. We haven't talked about. I'll start talking about that today. Okay, and then torque is related to. I'll show you guys how that relates to torque. Okay, and so it's Greek letter tau. And then now angular momentum, this capital L, that was a little more involved. I won't have time to get that today, but you guys see that's there. We're eventually going to get towards that maybe next week, maybe something like that. All right. So we're now looking at rotational dynamics. So think, do you guys remember here? Actually, here's a good point for the next slide. Right. This one you saw last semester, we focused on the top half. That's your kinematic motion. Right. But the bottom half now we're going to start to focus on. Right. So here. Last semester, when I said like how much inertia does something have, well, that was just proportional to mass. If something had 3 times the mass, that was 3 times the inertia. It's like if you kick a soccer ball versus if you kick a bowling ball, right? If something's like more mass, it doesn't accelerate as much for a given force, right? Now, in a rotational sense, it turns out that how much inertia something has is related to how much mass, but also where's that mass located? And I've got a really awesome demo for you guys here in a couple minutes. I'll show you guys, right? So this is the sum of mass times location squared, location from a pivot point. Great. So hold on to that idea. Show you guys some examples. Okay. The line below that, hey, look, it's Newton's second law of motion, F equals ma. Okay. Now, the rotation equivalent to force is something called torque. Right. You guys see this Greek letter tau, torque. Now, I'll show you guys an example right here, opening a door. Right. Because if I open this door, you guys ever wonder why is the handle of a door opposite the hinges? Right. Why not put the handle in the middle or like right next to the hinges? Because if you put the handle right next to the hinges, is it really easy or really hard to open the door? Really, really hard. Right? You apply a really hard force and almost nothing happens. But if I put the handle opposite of the hinges, a really tiny force opens the door really easy. Why is that? The physics term for that is called torque. And it's all embedded in this little formula right here. You see, torque equals R cross F. Okay, so the force I just applied opening the door, that was F, however many newtons that I just pushed with. But this R, that's a radial distance from the hinges. Okay, that's why you want the doorknob opposite the hinges, so you can maximize this R. You get a bigger torque. Okay? Now, if you have a torque on something that's rotating, because that's what a torque does, it causes this rotational type motion. Okay, that can result in an angular acceleration. So maybe the door could be like speeding up, spinning even, if there's a net torque. Okay? How much? Well, that depends on its rotational inertia I, which is how massive is the door, but also how is that mass distributed, right? Which we're about to see a table for. Okay. And all that line right there is really the rotational equivalent of Newton's second law of motion, F equals ma. In fact, if you take what you know from first semester, these linear values like force, mass, acceleration, and just very simply pop in the rotational equivalents, you get perfectly valid rotational formulas. That's one of the big pictures I want you guys to get away from this slide today. So instead of force, it's torque. Instead of mass, it's rotational inertia I. Instead of linear acceleration A. Now it's angular acceleration alpha. Boom, 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 just like that. You see that? Right. Now the lines beneath that are, let's see, I got momentum, mass times velocity. The angular version of that, if it's rotating, like a rotating turntable with mass on it, we call it L. So that's I times omega. Right. Okay, so P mv L I omega. Right. Again, we're going to see that one for at least a few days from now, maybe next week. Okay. And the very last line is the kinetic energy. Okay. Now these are both kinetic energy at the bottom. Okay. They're both in joules, but so left one is translational kinetic energy, 1/2 mv squared, which you guys know from last semester. The right one is like a rotating platform, rotating turntable. So I instead of m, omega instead of v. 1/2 I omega squared. Okay. Hold on to those ideas. We'll see them in the next couple of weeks. Okay. All right. So you guys remember this turntable? Here's turntable physics, how angular motion relates back to linear motion. That's a little bit of review. I put review on here. You guys remember these kinematic formulas? But again, this applied to a turntable. How far is it turned? How fast is it turning? Is it speeding up, slowing down, rotating? And how much time has passed? All right, so talked about that last semester. So just remember that's there. Okay. Probably saw all the rotation. Oh, some graphs. Here's a turntable slowing to a stop. Here's what displacement, velocity, acceleration graphs look like for a rotating situation. We did that last semester. Review. That's there. Okay. Okay. I forget if I showed you guys this one last semester or not, because this is one of these concepts, center mass, that pops up all over the place in physics, and different textbooks organize it into different chapters, right? So here, let's do a recap anyway. So how do you find the center of mass of a system? And this math says you very simply take a weighted average. Now, what's one application of center mass? Suppose I got two masses. You guys see this big mass A and the smaller mass B? What if I stick a stick right through them? And maybe the stick is very lightweight, like balsa wood, so I'm going to kind of ignore that mass. Okay? And I want to balance that on my finger. Like, where would it balance? Okay, well, it could balance at the center mass point. Or if I take this and throw it in the air and it's spiraling, like it's going to spiral around the center mass point. That's another application. Okay? I have some foam board cutouts that are all weird shapes. This will be an activity I'll do with you guys probably in the next week or so, where you hang the foam boards and the center mass always lines up beneath where you hang it. Okay? Okay, so how can you find this mathematically based on the masses and locations? All you do very simply is take a weighted average. Look at this. So if I got two masses on an x-axis, give mass times location plus mass b times this location, add all that up, divide by the sum of masses, that gives you the average location. That's it. Right, and this gold box at the top is the more generalized version of that. So if you have like more masses, my AP students have a textbook puzzle where they have like a 2D plane of plywood. So you just do x-axis and then you do the y-axis. Okay. If you had a 3D object, you could also do the z-axis. Okay, that's it. All right. I got a couple of sort of bonus slides slipped in here. I've showed this near the beginning, near the end. They're here, so let's just go and do them. So how do you define what's stable or unstable? So the physics definition of unstable, let's start with unstable on the left. If something's unstable, if there's any small displacement, then the object is going to continue to accelerate in that direction. You guys ever tried to balance a pencil right on this point like that picture? It's pretty much impossible to do that, isn't it? Even if you actually did get it and it stood there for like 5 seconds, like, well, I actually did it. Right? If the slightest little bit of dust comes along, like lands on it, a slightest little breeze, slightest little vibration, it's just going to fall over. Right? Same thing trying to put a ball on top of a hill, it's like nearly impossible. Right? So those would be unstable. If we go all the way to the right side of this, stable. What makes something stable? Well, the physics definition is if you give it a small displacement, it actually goes back to its original position. You got a picture hanging on a wall. Any object probably sitting on your desk right now, like that glue bottle sitting on your desk. If you give it a little tiny tap of it, it just goes back to where it was. So we'll call it stable. In the middle picture, neutral, like any ball rolling across the floor. Right? If you give it a small displacement, then it sets up, looks exactly like how it started anyway. So that's what we'll call that neutral. Okay, you guys got that? All right. This one is also kind of a bonus slide, but here, this is more like food for thought. This one can get really involved and really deep, but I want to show you guys something really cool. Let me flip over to my camera here. I bet you guys have a cell phone probably, right? You guys got a cell phone? Right. Now, this one's really, really weird. But here, suppose that this was out in deep space and I gave us the flip, start rotating. Could it rotate along this axis? It could rotate along this axis, right? Hey, if I spun this in space, it'd probably like spin for 1,000 years like this. No problem, right? I could also spin it like this. Right, and no problem, I can spin like that. That's no problem, right? Okay. All right. Now you guys ready for a really, really weird challenge? You guys got your phones out? Right. Try holding it like this and spinning it about not this axis and not this axis, but this axis right here. And I can almost guarantee that you cannot do this. You cannot make it so, now I have a really confined space here, so it's kind of hard to demo this, right? But if you try it yourself, I bet you cannot make a clean flip all the way around like that. Go ahead, try it, right? What it always wants to do is make this like weird turn in the middle, go like this. This goes by different names. Intermediate axis theorem, it's called. You just with a tennis racket. There's a there's a video on YouTube, Veritasium. It takes like I think like a half an hour to go through and explain this. Right? It's a really, really weird corner of physics. That's really beyond the scope of this class, but maybe I just want to plant that there for like food for thought. It's like oh, okay, so if that's there, that exists. If that really piques your interest, then maybe on your own time you click that. Oh, here's an interesting application of this though. You guys remember last semester this O'Neill cylinder? There's a reason that I made this O'Neill cylinder a really wide radius, but not very tall, like widthwise, right? Because if you go the other way, if you make it like a little skinny cylinder that's really long with a really tiny radius, right? That actually would not rotate in space. So maybe like, I don't know, 200 years from now when we actually have these O'Neill cylinders in space, don't like design it on the one on the right because that would never actually be stable. But the one on the left is, right? Why? Because it's really weird corner physics, right? Right, so there you go. So that's fun. All right, let's just go back to fundamentals though, because maybe most physics teachers, physics classes around the room, they might start with something maybe like this, right? So how much inertia does something have? Well, in a linear sense, it's just how much mass, right? But in a rotational sense, it's how that mass is distributed, where it's located. You guys see the left picture versus the right picture. And I have these in class, so I'm going to show you guys right here. Okay, I got a couple of meter sticks with each have a couple of weights attached to them. You guys see this one in my left hand has a couple of weights near the center. This one on my right hand also does, but they're on the far ends. There's one on the far end there, and all the way to the other far end. There's on the other end. You guys see it? Right. So each of these has a couple masses tied to it. Right. Right. Now, if I close my eyes and pick them up, well, since it's the same mass, they feel like the same weight. Right? If I shake them back and forth like this, linear sense, they feel like again the same mass, same inertia. Oh, because it feels the same in every way. But all right, you guys ready for this? All right, here's the weird one. What if I grab one near the center and I shake them back and forth? Ooh, now they're entirely different. You guys see the one in my left hand where the masses are close together? It's really easy to change the state of motion. That means not very much inertia. The one in my right hand, it's really hard to change the state of motion. That's a lot of inertia. Same mass, but different locations of the mass. So I'm going to pass these two around class so you guys can do exactly what I did. Grab them each near the middle, shake them back and forth. You'll feel a really stark difference there. Maybe this. Yeah, so yeah, you guys can pass this around, try this out. Right, they feel really different. So what's the math going on there? All right, so the math is, let's check this out. It says the sum of mr squared is this capital I is rotational inertia in a rotational sense. So let's say the one I had in my left hand here, say some mass at some distance r, so that's mr squared for that point. This is another mr squared from the pivot point I'm holding in the middle. Add it all together, it's 2mr squared, right? So sum of means add them up, right? How about the one on the right? Guys, if I slide those masses out, let's say by a factor of 3. Guys, if they're 3 times as far out, what's a factor of 3 squared? 9, right? So I got 9mr squared here, plus this 9mr squared gives me a total of 18mr squared. Guys, see went up by a factor of 9? Right? 2mr squared to 18mr squared, right? That means 9 times the rotational inertia. So if I'm trying to shake it back and forth, maybe it's like 9 times as difficult, right? And you guys can feel that too, right? All right, everybody good so far? Right. Now that's for point masses. What if you have a more involved shape? Let's look at this basketball. You guys see this basketball? You guys ever spin a basketball on your finger? You guys ever do that? Or maybe you've seen it. Take some force at some radial distance, maybe some torque to get it spinning, right? But how much torque does it take to spin the basketball like so much, right? Well, that has to do with how massive is the basketball, but also the fact that pretty much all the mass of the basketball is a spherical shell. It's all on the surface, isn't it? Pretty much on the surface, right? So how do you make sense of that? Now, what you could do is you could break this into a billion points. You could do mr squared for this, mr squared for this, mr squared for this. And they're all rotating about this central vertical axis, right? And you could add up all the little mr squared bits for a billion points. The aggregate effect ends up being a factor of 2/3 mr squared. You guys see that? Right? And you can prove that with calculus. I'm not going to do the calculus proof with you guys, but that's the math you need to show that, right? How about all these other shapes? Let's look at the rest of this table. So, okay, so I see my original point, which is mr squared, just like the last slide. Mr squared. Okay, sum of mr squared, single point mr squared. How about a ring rotating about this central axis here? Well, every single point on the ring is equidistant from that center. So the aggregate effect of a billion points all mr squared is just mr squared. Okay, so you get that. Okay. Ooh, a solid cylinder. Now, solid cylinder, some of the masses out this location are, but not all of it. A lot of the mass is actually closer to the axis. So it's going to be less than mr squared. And if you run the calculus, it ends up being a factor of a half m r squared. Right? Corn on the edge, a quarter. Right? Now, I'm not going to expect you guys to memorize this table. Same thing for my AP students. AP is not expected to memorize this table, but maybe apply the table if I give you the values. Right? Right. Okay, so we got all these different shape objects, and you can show the aggregate effect. What's the rotational inertia? Right? Right, guys good so far? All right, let's take that another step. Something called parallel axis theorem. What if these objects are not rotating about the axes shown in this table? Like, what if this basketball is like revolving around this axis that's parallel to its own central axis way out here? Hence, parallel axis theorem, right? All you do very simply is take the rotational inertia straight from the table. So for the basketball, it would have been 2/3 m squared. Okay. All right, so I got that down right here, bam, and say plus, and then md squared, where that d is the distance to that parallel axis, right? Just like that. So not so bad, right? A really common example could be a ball rolling across the floor. Guys, a ball rolling across the floor is not actually rotating about its own center of mass. It's actually rotating about this point all the way down near the floor, isn't it? Right? So you have to consider that. So I got 2/3 mr squared from the table plus m r squared because that parallel axis bit, right? Gives you 5/3 mr squared. Ooh, right? So if you try to kick a ball across the floor or bump a ball across the floor, or maybe it's rolling towards you, you're trying to stop it, then it feels like this much inertia, like 5/3 mr squared. Okay, it's a little more involved, but got that. All right. Yeah, okay. Let's go to torque. All right, just got a few slides left here. Torque. All right, this way I was just showing you with the door. Like if you look from above, this could be the door hinge on the left, and this could be the door handle on the right, couldn't it? You'd be like, this R could be the width of the door. Okay. And the wrench version is maybe I got this wrench, you're trying to turn this nut, maybe it's like rusted over. And so how do you get it to turn? Right. So you want the most torque you can get. I got torque as R cross F. So that's this distance R. Hey, if you have a handle that's longer, guys, a longer handle wrench, does that make it easier to turn the nut? Yeah, sure does. Also, the harder you push it, so the more force. And one more detail. You guys see this cross product multiplication? Right? Cross product means you only multiply the perpendicular components. So like if I was pushing into or away from the handle, like parallel to the handle, that would be no good. That would never turn anything. Okay? But any perpendicular component. Okay? So if you can make this angle theta close to 90 degrees, that will also help maximize the torque. Right? So you got that. So R F sine theta is the way to write that cross product. You guys got that too? Okay. Right. Now the other perspective on torque is that torques cause angular accelerations. Now notice I'm calling this a net torque. So maybe you're applying the torque R cross F. Maybe there's some counteracting torque by maybe, again, if this nut's like rusted over or you consider the friction, maybe you subtract that out. So you get some net torque. This is going to cause this wrench to accelerate in an angular sense with this alpha. How much? Well, it depends on the rotational inertia I of the wrench. You got it. Okay. So you guys good? You guys got torque. All right, so behind that. Right now, in this class, here, let me go back. In this class, we're going to talk about torque mostly being like clockwise or counterclockwise. But depending on where you're standing in the room, in front of it or behind it, your perspective could change. So there's a mathematically better way to handle torque, which is with this right-hand rule and with cross products in matrices. This is maybe a little bit beyond the scope of this class. Or I don't know. Or I don't have time to go over this today, maybe. But maybe in the next few days, I can show you guys an example of cross product, right, just to kind of see how it works. Right? If you're going to go like a hard, like math, engineering, science type route in college, then no cross products. Did you guys do cross products in math class? Maybe algebra 2, possibly. You guys do? Yeah. Oh, okay. You did do cross products. Yeah. Torque is a cross product. That's all. Right. So did you guys do these matrices like this? You guys see? Oh, good. Oh, good. I'm so glad that you guys have, because I usually have students in the past and some of them have never seen this. Right. It's kind of good to know. You can do some really good math with this too. Right. All right. This is a lab we're going to do one day. I'll have this rotating system, and this weight pulls down and it rotates it, and we're going to figure out what's the rotational inertia of the system. So plant that idea today. Look for that in the future. Right, here's the last slide I'm going to do with you guys today. All right, just to round things out, is go back to equilibrium. Now, last semester I told you equilibrium, the condition for that is the sum of the forces is equal to 0. And then you could take that an extra step and say, okay, well, that's also true along each axis. So on a 2D plane, x and y axes, in 3D, x, y, and z axes. Right. Now, starting this week, we're going to bring in the other condition you need to have true equilibrium, which is that the torque also sums to 0. If you're going a civil engineering route, you want to build some large static structure, this page right here is the starting point of anything you can ever design and build. You want to make sure that everything sums to zero. All the forces sum to zero, all the torque sum to zero. And then you can use those conditions to solve for, like, what's the tension in this little component, or this bar, or this beam, or this column, or what's the compression here, right? You can solve anything and figure out how much concrete do I need, how much steel do I need, right? But this is your starting point, right? All right, so I got a lot more of these slides. It could keep going on, but that's about the time I had to at least find some ideas. Rotational inertia and torque. You guys got those? You guys got torque equals I times alpha, sort of Newton's second law of motion in a rotational sense. Okay. All right, so let's take the rest of class and put together the rest of this Geneva drive. Right. It's the story. Okay. All right, so here, I got this model from yesterday. Remind you guys what we're headed towards. We're trying to turn this continuous motion in my right hand to this incremental motion in my left hand. You see this in clocks, like tick-tock. Okay. You can see this in like old film projector, like turning a continuous roll of film into 30 frames per second. You might see this in an assembly line at a factory. Okay, so there's some applications. Okay, and we said the component parts, which we have together right here, are got a couple of wheels. I did cut the teeth in one of them at the end of class yesterday, and see, we got all these cylinders. We cut some feet into make these pegs, and some of these we turned into axle systems. So I got this axle system here. I got this axle system going on right here. Okay. If you keep pace with me, maybe you also have all those pieces, and everybody works a little bit different pace. That's okay. Maybe you're catching up there. All right. So I think it's going to take me about 15 minutes to put the rest of this together, and we'll have another 15 minutes that you guys can keep working. Okay. Okay, like the teeth. Right. Okay. Yeah. So how I made this, there's no one exact right, right? You can do your own thing. I had 8 teeth on mine, which is 45 degrees between each set of teeth. And I did 1.5 centimeters by 1.5 centimeters. Let's see if I unfold this. Right, that's what I did. I went 1.5 centimeters in, 1.5 centimeters wide, right, and then cut a square and do that. Right, that's been working for this project. I've been doing each class about the same, so that's been a pretty good set of measurements. Okay, if you want to make it a little bit bigger, a little bit smaller, if you want to cut the gaps like trapezoids, make the teeth look more square, it might be. Yeah, you can play around with it and kind of experiment around, see what works. But this design should work. All right, so let's try that. Now, if I want to make mine look exactly like the model, I do see the one that I hand turn has this handle in the middle, and these 3 pegs. Three, I'll do 3 just to match the model. Okay, guys, if I have 3 pegs, let's get the measurements right. If I want it to be symmetrical, so this thing balances, like the center mass is also the geometric center. How many degrees? Like, what's this angle between these 2 pegs? How many degrees is that right there? 120. That's right. I need 120 degrees. 120 degrees. I don't know if my model's exactly right. Okay, sprinkler. 120 degrees. So I think that's the next part I'm going to do right here. Maybe I'll put a peg right here where I got this radius marked out, and I need to go 120 degrees. You guys have protractors on your desk. I'm going to mark out 120 degrees just so I know the location of the next peg. Right. Bam, right there. And then go 120 degrees the other way. 120 degrees. Looks like bam, right there. Right. And then just double check, make sure that the angle between those 2 that I just marked is also 120 degrees. It should be. And see, zero that out. Oh yeah, nailed it right there. Nailed it. All right. So this point, this point, this point are each 120 degrees from each other, which means that when I glue these pegs on, the center of mass of the whole system will also be the geometric center of the circle. So it'll balance, and yeah, probably about as good as I can get it. All right, let's try that out. All right, so circle these on. I know these 4 pegs I made identical yesterday, or identical as they get. So glue this one right on the center, and this will become the handle. Sure, I got that right. That is right at the center, right there. All right. I think if I balance this on my finger, it should balance right at the center. Oh yeah, right there. It balances right at the center. Right there. Right. Okay. If I glue these pegs on exactly where I put those dots 120 degrees apart from each other, that should continue to be the case. All right. So see if it still balances right at the geometric center. Is the geometric center still the center of mass? Oh yeah, right there, still balancing. It was balance on my finger, like right at the center. Yeah, okay, right there. All right, so I got that. All right. Got to bring in these axles right here. Okay. Now, remember, here, just make sure these still rotate. Yeah, so that rotates good right there. This rotates good right here. All good. Okay. I forgot to this yesterday also. Then I do remember that. See, you started out as each a couple of squares. The squares are the same size. Rolling the cylinders, they look the same. But then the one in my right hand, I cut the feet a little bit longer than the one in my left hand. You guys see there's a height differential? You guys see that? The one in my right hand's a little shorter, and the one in the left hand a little taller. You guys see that? Okay. And the reason I want there to be a height differential is, I can show you with my model. Back to my model. Okay. You guys see how the pegged wheel is sitting a little bit underneath the tooth wheel? Right? So these pegs come up from underneath. Right? You can do an upside down version of this too, where if you swap the axes, maybe you just flip the peg wheel upside down. It could also work that way. That's good too. But I like this way because you can see exactly what's going on. Right? Okay, so there's definitely a height differential going on right there. Right? The peg wheel is sitting lower than the tooth wheel. Okay, so I'll keep that in mind. And how about looks like the taller one, I want to glue this half of this axis right in the middle of the bottom side of the toothed wheel. Half that axle. All right, see, does this rotate? Oh, look at there. Oh yeah. Go. And this is just going to be glued to the spaceport, and then that'll be that one. All right. Let's try this other one here. Work on story. Let's rotate. See. This one's a little tighter, but yeah, it's to work. Yeah, that'll still work though. Yeah, that'll work. That works pretty good. There you go. All right, coming together. All right, so I'm getting real close to the end. Okay. Last thing I got to do is make sure that these two wheels are like axle to axle are correctly spaced away from each other. Right? Because if they're too far away, then maybe the peg doesn't even reach the teeth at all. That would be completely pointless. Okay. But if they're too close together, you see how like right here, the just like lock and like not even move at all. Right. So I need some kind of optimal spacing. Okay, so that as this peg leaves this gap, the next gap is already aligned to accept the next peg, and it'll move on like that. So I think a good way to do that is to glue down one of these and then slide the other one in place. All right, so maybe I'll glue down my peg wheel first, since that's going to be sitting, it's supposed to sit a little bit lower. So the other one can just come in right on top, which would probably be easier to work with. Right. So just find some random place right there. It's probably pretty good. Right there. Bam. There comes in. Okay. Yeah, that's looking pretty good. That'll rotate. Okay. All right. Now my toothed wheel. So, yep, sitting a little bit above it, just like I need it to. Okay. Okay, I got to find the optimal location for this. All right, so let me do some trial runs here. That looks like it's a little bit too far away. Let's get a little closer. Let's try it right here. Sometimes it's just a matter of like a couple of millimeters. Ooh, that might be a tiny bit too close. Back it up a tiny bit there. Let's try that. I'm gonna mark that right there. Okay, great. Should bring it down a little bit. All right, let's see what that does. And if I miss a little bit, then I'll try to still scoot it around while the glue is not completely dry. And if somehow that still doesn't work, then what I could do is modify the teeth after. So I can always shave off a little bit from the teeth and open the gaps up a little bigger if I need to. If you need to go the other way around, if you have some scrap paper around, you could go back and make the teeth a little bigger, right, which I haven't had to do, but right, just think ahead if you really mess up on this. But see, okay, so I think that's probably where I want it. Let's see if this works. Ooh, a little too close. Let's back that up a little bit. Yeah, that'll do it. All right, look at that. It goes all the way around. Yep, that's exactly. All right, so press that down right there. Yeah. Oh, yeah. All right. All right, so there it is. Oh, and perfect. We got 20 minutes of class left. Great. Great. It's gonna work. So the rest of class, these last 20 minutes, I will walk around, help you guys complete these projects, take about probably just about that amount of time. So that'd be perfect. Of course, I won't see you guys tomorrow. Hope you guys enjoy the radio story tomorrow. And then if all goes well, then on Thursday, we will pick up with rotational dynamics.